My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. This is an advanced course, and I'm talking today about scalability in HPC, high performance computing. So that includes all kinds of supercomputers and neural networks and different kinds of implementations. And so we're going to drill down into all of that. Share a screen. Well, first behind me, you can see the agenda. So we'll look at SMP, MPP, and vector. So symmetric multiprocessing or shared memory processing, as it was known several decades ago, which is more descriptive. Massively parallel processing, where you have a lot of nodes all doing their own thing, and then there's some kind of communication going on between them. That's the future coming, and there's not quite as much of a bottleneck. SMP is what we're used to in most cases now. And vector register, which applies to linear algebra, matrix manipulation, grand challenge problems. And so that's a thing in itself. And then the Flint classifications of single instruction, multiple data, multiple instruction, multiple data. We won't talk about SISD or the multiple instruction, single data systolic array, which is actually out there, but it's somewhat of a theoretical thing. Then grain sizes, so how you break your problem down into pieces. And two things with that: degree of parallelism, and also how you can pack grains and scheduling, including dynamic scheduling, but first of all, just static scheduling, and making use of your parallelism, whether you have multiple dual pipelines in a superscalar or multiple cores or processors in various architectures. And then static versus dynamic architectures, and looking at what's actually most scalable there. We'll talk about that and the different kinds of dynamic. And then cache optimization. I won't drill down on a lot of that, but it also lends itself to scalability too. We'll just touch on that. And then neural network hardware, where ASICs, a couple neural network processors I designed 30 years ago, and then into the future now with GPUs and CUDA cores and such, and also a novel paper that the students have on a particular architecture. Modularity for simple computation on a larger scale, doing a lot of things and cutting down on the bottleneck of communication. And then in FPGAs, just the intro part of that, where we just talk about the modularity of the FPGAs and the basic cells and what they look like. And then we have the research and teaching assistant for the course is doing a whole lecture on that on Monday. So that's just part one here, and we won't record that. Well, I'll probably record him, have his separate recording on YouTube. And then IBM part one, and things that I worked on long ago, 30 years ago, or over 25 years ago in IBM, System 390, and some other things too, the Parallel Sysplex and some original things that had scalability as an issue. Okay, so let's share screen. Pause for a second here, actually. Okay, resume recording now. So now I'm going to share a screen, and we're going to look at some things. So what you see here is my website, and I've done a number of things over 60 years. I'm not going to talk all about that, but in the computer engineering and robotics, and we're in here now, and we're talking about this course that we're in right now, which is this Parallel Processing Advanced Computer Engineering Lecture and Lab. We're going here, and the first thing we were talking about was scalability, was the MPP, SMP, things that the students know in here from other courses, lower courses, and just quickly go over that, how that looks. And so different architectures, single processors, just a cache and memory. There's levels of caches, but in this simple architecture, a processor, memory, and some cache squished in between. And then SMP, symmetric or shared multiprocessing. You're sharing a memory. So right away, you should think about some kind of lack of scalability there. Although, I guess here's the place to talk about this a little bit. Amdahl's law, I'm not going to put that up here, but it's the law of diminishing returns, where any optimization, if you're sharing memory, you can only have so many processors trying to grab or manipulate certain data, and it only scales so high. Now, there's ways of that bottleneck has been broken a little bit, but it's still holds that you can only scale so much when you have one resource that everybody's sharing. The way it's been broken a little bit is by treating the processors like network nodes and then doing some kind of packet routing sort of protocol like you would see on the internet. And they've shown some improvement with the number of processors compared to the diminished returns that would happen otherwise, but not beating the ideal case. And then vector registers. So this is anytime you're doing linear algebra, matrix manipulation, molecular modeling, astrophysics, anything. Most of the grand challenge applications are linear algebra, matrix manipulation, and anytime you multiply two matrices, that's a row times a column, that's a vector operation. So you need vector hardware in parallel. And then MPP. So this really is the wave of the future. Now, this is also, you see below here, what a computer network looks like, except it's in a box. So it's essentially a computer network in a box. And you have some way of dynamically connecting everything to everything else. And that's a key thing here. So, static, we'll see in a second, a review that static is not as scalable as dynamic, but then there's variations of dynamic that aren't so scalable either. The bus is a dynamic architecture. It's not as scalable as a crossbar switch. Static, by its nature, is not going to be as scalable. So we'll just take a quick look at that. All right. And then the Flint classifications are down here, and you see this is just a simple single instruction, single data, but single instruction, multiple data, and also the multiple instruction, multiple data. Okay. Let's skip that through this a little bit. Sorry, okay. And then there's a number of things we're going to drill down into in a second here. And these are other chapters that we're going to look at separately. I'll just pull them up. Scroll through all that. There's some IBM stuff up here that's no longer classified stuff. After 30 years, I'm sure there's statute of limitations. These are not competitive machines anymore, but this was IBM confidential back then. And other things. Microprocessors and microcontrollers I won't talk about here as much, but a microcontroller, being a simple little device, should be a scalable, nice little thing for cheap, although it really doesn't have the communication protocols that you can do with a good processor. So we'll just kind of go down. Anything else in there? I'm back to the syllabus now. The next thing on our list was grain sizes and degrees of parallelism. And so if I asked this on a test, I would have all these subparts and a couple of points for each part saying something about it. And I'll be as specific as possible, but leave you some leeway to get points if you don't remember exactly what I was asking for. That's the problem with being too specific. People don't remember, you get 0. If I ask for something general essay, there's lots of ways to get points. But it's a little harder to know exactly what I'm expecting. And quite frankly, I don't sometimes. I curve them and I look to see what people have extracted, which makes it even more difficult for students to know ahead of time, but I think it's a good educational exercise. So parallel processing. So now we're in here and we want to look at dependencies, data. Well, we won't go into all the details of that, but the grain sizes and degrees of parallelism, as well as scheduling and partitioning. Go through all this. These are whole lectures. Let me just get this centered a little bit here. Make it hard to read though. Just skimming through a lot of things here. So degrees of parallelism, you have an ideal case where there's no hardware constraints, right? So that's as scalable as you can imagine because you're not even thinking about the hardware. Just assume you can load everything all the time. And if you need multiple calculations going on, just do them all simultaneously. This should be a beautiful thing, but completely unrealistic because you have to consider the hardware you're on. And then comparing that to different types of things. So in this case, we have a two-way superscalar processor with 2 pipelines. And so now how's this going to scale? Well, it's only 2 pipelines, but there's dependencies between it. So, but if you're doing this on multiple places and multiple different cores, You can quantify it a little bit, degradation for the increase in parallelism. But as one single core with two pipelines inside one processor, with certain data dependencies and also hardware constraints, you have a degree of parallelism that speaks to scalability. That's what it's all about. Now, this is two cores. This is two non-superscalar processors that are talking to each other. So the data dependencies have to be worked out because they're using, they're both calculating this A and B. So they have to talk to each other to get the shared products passed back and forth. And in SMP case, you're going to have IPC doing that through memory. There's other kinds of multiple processors in the MPP environment, and then there'd be a different kind of communication protocol going on. And we want to look at that, think about that. But for now, just assume that, okay, in this case, and the students did in the last test, that you need to store something so that the other the other core can then read it. You need to store something in memory so the other core can read it, and vice versa, because you're, again, each taking pieces that each of these processors are taking pieces of these equations that are used by the other cores, and then you have to share them. Otherwise, it's just redoing it. I know you can do no duplication where you don't want to wait for the other core, and then you could just have some redundancy. But you should remember, if you're filling an idle spot on a core, you could be filling that with the next process. So it's not necessarily all idle. So no duplication has to consider what else could be in there other than something that would make more efficient the problem you're presently working on. And there's another problem, was on previous tests, and the students had a similar thing where I added another variable in the last test. It was directly from all this. And then they were asked to compare them. Actually, more importantly, another thing down here was scheduling. So partitioning and scheduling. So then your grain size. So, linear algebra has fine little calculations in it of the partial products, the products of terms and your vector operations. And so that gets pretty fine grained. And then coarse grain is a different kind of thing. But if there's a lot of communication that's required between processors or threads even, threads ideally are not dependent on other things, but you still have to stop and talk to each other. And so the grain size of the problem needs to be defined. And then there's a lot of detail in here, but we want to look now at packing, grain packing. So you take a problem and you break down the problem into little bitty pieces, and then you see how to optimize the flow and the critical path of things and dependencies. So, again, critical path while lumping things together that can happen in parallel, then making a coarse-grained graph, and then actually scheduling. This is not dynamic schedule, it's still static. So so we're looking at two processors now, and packed or unpacked. Grain without grain packing and then grain packing. And so you're increasing the parallelism and making it more scalable. And then this is just the same thing. Again, the more scribbly version. And then another problem here with actually matrix manipulation of one matrix times another, and then a second operation of summing all of the elements here. And this is not unsimilar to what you need to do in neural networks. And if you had cores that could do this individually, this kind of thing, or something close to this, you can accelerate a neural network learning because it's full of matrix manipulation. All the neurons are represented, neuron weights are represented by matrices. And so this particular problem is, we're doing this linear algebra thing, and we're doing grain packing to make that work, and scheduling, and then looking at that, grain packing and scheduling optimization of that. And then we go back and I might ask this question again on the final exam. I only got a couple of people that answered it semi-correctly, or actually pretty good in the last test, but this is comparing degree of parallelism and grain packing together. Scheduling, and then dynamic scheduling out of order execution. We just touched on a couple things in there, but that's a key in a reservation station, doing things out of order. If you have something computationally really expensive, you, in a way, let things jump ahead and get executed because something's going to take forever, and then you use your parallelism to do that, do something that's fast before something, or start it or let it happen simultaneous to what's slow, and don't let the slow things top everything. And then there's algorithms for doing that kind of thing. It's all dynamic scheduling, and the scoreboarding all falls into that. Okay, keeping track of all that. Then the next thing on our list was cache optimization and cache design. So in here, we have this, which is kind of hard to look at here. But the whole idea of optimization, we talk about this in Amdahl's law too, but it also applies to cache block sizes. And like how much stuff do you grab at once when you have an error? So I asked on the last test about cache and temporal versus spatial locality of reference and how that applies to what a cache does. Well, the temporal is you just did something, so you want to do it again. And if you can do it in a faster little memory, great. You just sped up the machine. The spatial has to do with when something doesn't work right. So the spatial is when you have a cache miss, and then you want to go get a big chunk out of memory, and you want to drag it first to the processor that's looking for it, and then put it in the cache. And why a chunk? Why not just get what you need? Well, because in all probability, because of spatial locality of reference, you're inside a code loop, or you're in a data array, and you're in all probability going to need what's spatially, adjacent in memory, physically located next to your code that you just executed and had a cache miss, or your data that you just grabbed and had a cache miss. Grab more stuff, and then you'll likely have increase in performance. But if you grab too big of a chunk, you actually have a decrease in performance. So the same kind of law of marginal return, diminishing marginal returns applies to optimization of number of processors, or depending on grain size, the degree of parallelism you can do with code, depending on how much parallel hardware you have versus not parallel. And then the students learn all the mapping here. I'm not going to dig into all this. And there'll probably be a test on the final, but one of these actually designed this, but I might even tell you exactly what I want it to look like ahead of time, or some hint. Okay, so the next thing will be neural network hardware. So let's go into that. Now, firstly, this is all part of another course that I teach. So I'm not going to, but the students in here are designing a neural network module, or a neuron transfer function as part of the CPU, little CPU thing that they're designing. Little, it's difficult to simulate anything, but I'll show you that in a second. Or actually, I can show you right down here. So, so they're designing this architecture right now, and these are 4 parallel scalar functional units, and then 4 vector register units, as well as 4 neuron transfer function units. And so this, ideally, these cores, these are simple cores. There's no floating point in here. This is not too far off of what you would see simple cores doing, the CUDA cores or anything scaled with simplicity and good communication and scalability, instead of lots of complexity and lots of space taken up, where you can't have several thousand complex cores on a on a process, on a board, even a graphics board. So anyway, this neuron transfer function. So there's a whole course I teach in this stuff, but also has robotics in it, so it's overloaded with stuff. So I'm not going to go through all that, but this is a whole course in robotics, automation, machine intelligence, and you can see in there they learn all kinds of stuff, including some introductory examples in doing deep learning examples using MATLAB toolboxes, and just scratching the surface of how to do CUDA courses. We have a whole program now, and a professor teaches a whole sequence of courses and that stuff. I don't want to be redundant, plus that's another path. But in here, we're designing some hardware, a little bit of neural network hardware, so you have to have some idea what's going on. Some of the students here have had the other course I just showed you, some have not. So I just want to very briefly dig in here. So before I go into this one here, which is this is a book chapter of drafting of a couple draft chapters of a book I'm writing, and then this paper is in that. I just want to do little history thing here real quickly. And this would be the intro chapter to that book. And there's a ton of stuff in here, but the students in here, this is all I really want you to do, is a simple threshold logic unit. Now you could do this rectified linear one that I'm going to show you in a second, but you don't want to do this sigmoid in a class project, and I could show you why in a second. Why not to try to attempt that? So this is just the threshold. You have multiply signals coming in times weights, and then the thing either triggers or not if it's greater than a threshold. And so this is a threshold logic unit. And yes, it was 1940s. McCullough Pitts came up with that, but it really wasn't until down here with the perceptron. Here, yeah, perceptron, where somebody actually used it in an adaptive control way. So in control theory, those of you, Dr. Strato's mastered in control and did his PhD research in adaptive control. That's actually one of the definitions of cybernetics, by the way, if you wonder what cybernetics is. It applies to both human control systems as well as machines, and it has to do with changing the behavior of something based on adapting, on errors. And so now we're using a threshold logic. Now you don't have to go -1. You can just go 0 or 1 coming out, or you could do it like that. But so, if you look up here, this is the simplest thing. It's either 1 or 0, depending on some threshold. And I'll leave it up to you to do that. Now there's a ton of other stuff in here I don't want you to strain too much looking at, but the actual implementation is when the Amdahl networks and everything else, the whole history of Minsky and Peppered saying that you can't do nonlinear separable problems using the single neuron perceptron. And yes, that's true, but it's dried up funding for a while until the 80s, and McCullough or Rumelhart did back propagation. Hopfield was doing stuff there. He's a physicist. And then here, these are the two different kinds of things. So this is the hard limiting thing. Again, you can just do 0 or 1. That's the easiest. We'll look at one that it's called a rectified linear unit, where you can actually do something a little different. And it's sloppy in a sense. It actually can cause neurons to die and lock up, but you have millions of them now, so you can do traditional learning and not have the precision. And that's how these things end up working. It used to be 30 years ago, you couldn't have that many neurons. There's supposed to be a T in here. It has to be continuously differential. And so again, I don't want to look at all that, but learning how neural network works. This is just the algorithm that derives from all the calculus. This is how it all works, and I'm not going to get into all that. So yeah, I just want to touch on that for the students who are doing this as a lab. And then, if just FYI, in less than 60 seconds, I promise, I'll show you how it can get hairy very quick. So bottom up versus top down. This is a whole other thing of spiking neuron biological things. We'll look at that. But down in here, if you're trying to do do something different with the transfer function, and it's accurate in a certain range, and you want to make it all digital by doing some kind of polynomial instead of this transcendental, which is very hard to implement in high precision without being costly, and especially in parallel, then that was the idea. So I was trying to find precision using numerical methods of different polynomial approximation methods here, you'll see, and show that worked, and blah, 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 blah. And oops, there's something down here that shows it better, what actually I'm trying to do. Where is it here? Wait a minute. Hold on. So you can see it. Yeah, right down here. So the neuron transfer function is typically like this. And the slope of the curve is key here for neuron learning. And so you'll see it peaking when you do your gradient descent learning and your multivariable chain rule. You'll see it peaking right in the middle here. So it tells you there's a range where it really needs to work best. And it's based because the slope is where the learning's happening. But when you start going horizontal, pushing towards the asymptotes, then it's almost irrelevant. Well, where exactly? So I did this thing called a clipped sigmoid and showed that it worked through simulation. And that I filed that in the patent office in 1992 as part of the chip design. But anyway, that's a whole different thing. And so anyway, don't try to implement this. Just try to do something simple. So hopefully that was less than 60 seconds. Because that's a whole thing in itself. And then we're back down in here now. And so that's all I want to say about neural network stuff. Well, one more thing here. This, where's the font on? This, I didn't print this out. I printed a paper up here that I just skipped over. I got to come back to that. But that was, I probably should have done that before the neural network. All right, maybe I should move this down lower. But let's just, while we're talking about neural networks, look at this. So this is called deep learning using rectified linear units. And this is the transfer function. So it's just nothing until you've got a weighted sum that's positive. Now, what happens if it drives negative? Then certain neurons can die and not recover, but you don't really care because you have enough of them. And I would say it's sloppy. I mean, if you can actually do things simpler and faster and get better results, and it's not as elegant as following nice, beautiful gradient descent behavior. But if you've got millions of neurons, the human brain does a similar thing. We don't use all of our neurons, and we do stupid stuff with them. We bang our heads, we drink booze, and kill a bunch, and it recovers. And then the students have this one here. Now, I already handed this paper out, but I don't want to go a lot into it because the main idea here is, and you'll see I talk about a number of things in here, but the main idea here is they've made a simple internal structure of this fontan, and it has associative storage. It kind of works like a cache. It has a lot of cells talking directly to each other. So they talk about breaking the von Neumann bottleneck, which, how did we miss that too? We skipped over that. Well, I'll go back into that, the static versus dynamic. But if you can have a lot of things talking to each other all the time and not going through memory and having a dynamic interconnect architecture, then that's ideal. So there's a bunch of stuff in here, and I'll let the students read that, but I think we're going to just not try to memorize all the details of this. But the essence is these are unique little cores that can scale quickly, and they've proven that it can work very nicely for a number of different things. And they even said they could prototype it on an FPGA, but the idea is to implement it in the real world in a core for production. I mean, in cores, on a board, in like a GPU environment. Okay. So I won't go into all that detail there. I'll let students read through that. But it's a novel kind of thing. And they also talked about ways of scaling the silicon, make it work a little better. But I can tell you from working inside IBM, you got to watch out thermodynamics. You start doing things three-dimensional, the heat's going to stop it from overclocking like you would like, or even clocking faster. They just throw that in there. Okay. Let me go back. Let me just stop sharing for a second. So you can see behind me, we did SMP vectors, SMD, grain size, and we skipped over number 3, static versus dynamic architecture. I want to go back into that. We went right to, that was an accident. I went and then going to cache optimization, block size, and we had neural networks. So we did that. So we've done 1, 2, 4, and 5, but we have to go back and do 3. So let me go back and do 3. So 3 is our interconnect architectures. So it's all about scalability. And so what's going on in here? It's readable. I apologize if it's itty bitty tiny on YouTube, but we're just skimming over things. You can get in the PDF, PowerPoints with embedded audio. This, you ever see the microphone, there's audio on there. That's all accessible. Even though I don't put a link, I'll put a link to the PDFs in the YouTube comments. But if you want a PowerPoint, you're welcome to use it. I mean, I didn't put copyright labels on this. I have copywriting some of my stuff, my other stuff. I'm writing a book on something, but I actually write 2 books, but the one I'm going to sabbatical. All right. So this is static. Okay. Now nobody yell out in the class here, but what's the problem with completely connected static? You should see that that's not going to be feasible to go to thousands of cores, is it? If everything's permanently connected with wires to each other, could you even do that? So, static is just not going to be as scalable. I mean, just accept that as a fact. And there's a bunch of scale, here's things the students did. And then you measure it. And of course, there's relative differences in the scalability and optimization. They want to minimize the bisection width here, right? The cross section through it, how many wires are going through that. You want to maximize, or you want to minimize the bisection to minimize required wiring, but you want to maximize the bandwidth for communication bandwidth, right? You want more connectivity if you can, but these are static. Remember, these are static. These are static. So, okay. This is just other stuff there. Static interrupts. This is all preliminary courses, packetized stuff, wireless communication. That's just other stuff. Scalability on static interconnect architectures. And I'm not going to quiz you exact things here, but these scale, and the number of nodes, some scale better than others, right? And you know how numbers work. You can see what's more scalable or not. Now, dynamic. So dynamic, you need, because you need to be able to connect everything to everything in many cases. But a bus is not better than, for example, a crossbar switch, because you still have this shared resource and you need a bus controller, and you only can have so much traffic on this pathway at a time. So, somebody's grabbing the bus at any given time. Now, of course, you can have some parallelism in the buses, but for the most part, that's not the most scalable dynamic. It's better than static, but scrolling down here to the dynamic architectures, here's dynamics, here's dynamic. These are somewhat novel things. The crossbar switch, where you have a whole bunch of processors, a whole bunch of memory, or processors, and they can talk to each other, have their own dedicated link at every given time. And these are typical optical connects, and IBM was optical. So that's a general thing you could say in a sentence. You need to get so many points for talking about each of these things. So, number 3 in our scalability and high performance computing and neural networks is static versus dynamic. Say something intelligent there in a sentence. Well, static's never going to be as scalable as dynamic, but within dynamic, the bus is not as scalable as a crossbar switch. And that's almost full points right there, unless I ask for a sketch or something. And then Parallel Sysplex, I already mentioned that. So that's connecting everything to everything. So we did that. That was existing 30 years ago. It still exists. And these are Z series, by the way, now. So this isn't ancient history. These still are alive and still costing $1 million and still selling well. And then scalability of all that. Okay, so now we're back on track here on the stop sharing for a second. Behind me, we did now 1, 2, 3, 4, and 5. And then we want to finish with FPGAs here. I'm talking for almost an hour, so I want the students to have time to work on their labs. We only have one more lecture class next week, and then review for final. And then we've got to finish projects, and not just for me, but for everybody else in the world. So share again. FPGAs. So now our FPGAs, we have custom manuals here and a teaching research assistant working on dedicated things. I won't play his video for you, but I think I'll play it for the students because I already have it on YouTube, so I'm not going to put it again in here. But FPGAs are scalable little things. So let me show you back in the very beginning here when we first started making lab manuals in 2002. And somehow this little diagram fell off the radar here, but they're basic. This is a basic idea of FPGAs. We have a lookup table, LUT lookup table, and then it has some, it in a collective way mimics the behavior that you want from the actual logic or code if you're working in hardware descriptive language, which should go right to gate level design, but it doesn't necessarily have to if you don't need the speed. But if you really want the speed, then I talk to the students about that in here, that they really need to work at the circuit level. Let me just show one thing real quick right here. So if you go in here, this chip that you see right here, that chip, and I'm just going to zoom in close enough here, but at some point you need to design, these are clock drivers here, not just driving the capacitive load and making all the wires laid out by hand. You're sizing, you're really controlling all the clock signals at the gate level. And so, I did individual subsystem research and, analysis of timing, rise times, fall times, and how fast we could switch it. These are actually capacitors too, doing a special kind of network. But even not, purely digital stuff has capacitive load. You store charges on gates, you have capacitive loads on wires you have to charge up. Yeah. Okay, so back where we were, and here, this will by, and finishing up here real quick. So students can do their lab work in this course. The last thing we had on the list there was IBM stuff, and so I won't even open up half of this stuff here, but processor design starting with the 9000 series in that whole, and so this is 30-year-old paper in IBM, and IBM has several journals of their own inside. IBM at the time had 500,000 employees and 9,000 PhDs, and they're not much off of that now. And for a while, I have to verify this, but they had more patents than all the other companies combined at one time in the history. I don't think that's the case anymore, but so we'll look at all that and the scalability, a number of scalability things. So multiple cores, interleaved cache, shared caches, as well as independent caches. And we're going to look at this on Monday, and then out of order execution units and a number of other things. Translation, look-aside buffer, hash, virtual address translations, separate instruction and data caches, lots of stuff. This is 30 years ago. And then one last thing on scalability here. Let's see, the Parallel Sysplex, is that in here? Machine evolution. Let me just look real quick. This is machine evolution. This is the history thing I put together. I'll go over on Monday. Let's see if there's anything worth mentioning in 2 seconds in here. It's too hard to focus on all that, but there's lots of things in here, switching from air cooled to water cooled, and how we did took a performance hit on purpose because people didn't want liquid cooled headache anymore, trying to run their country, their government, their military, their banking system with these liquid cooled machines. And then the Parallel Sysplex, I didn't zoom in on it here, but so this was really scalable. So we could do you could, first of all, run the machines that I was working on with multiple images. You could partition the machine to be like separate computers. So it's parallel in that sense, where the one machine could act as several computers and run like, for example, right up the road here, the entire military payroll is on one machine. Somebody gave a talk on that 20 years ago here, and each branch of the military was partitioned into a different part of the machine. And then beyond that, that's not with the Parallel Sysplex. Then the Parallel Sysplex, you can take this picture of it here, but you can connect a bunch of different things, not just IBM things. You can hook up Sun workstations running Unix type environments. You can hook Silicon Graphics terminals. You can hook Cray supercomputers and others. Anyway, okay, so this is scalable stuff we'll talk about later. Okay, and one last thing here. I think I'll just start running here for the students is the FPGAs. We're teaching and research assistant. This is already on YouTube. I can just bring up the YouTube channel. I'll show that real quick here on my YouTube channel. Look at the playlists. So I have intro high-tech lectures and 43 lectures for a 47 now for an intro class, and then high-tech lectures, advanced. And here, so go in there, I have architecture and other things, student projects. So down in here, we're going to play now what our teaching and research assistant made. FPGAs using Verilog, HDL, and gate level simulator and waveforms, which was one of my pet peeves for a while. I thought we lost some of that, but apparently we didn't completely lose it. We just need to have the facilities here to run it hardware-wise. But you want to have waveform analysis and be able to see gate level circuits generated by your FPGAs, equivalent ones. Even though they're using cells that aren't really doing that, you want to see equivalent circuits. And then some idea of waveform timing traces, even though it's probably not exactly what's going to really happen when you do it without the FPGA part. anyway, so there's only 9 minutes. I think I might just nest it inside of this one too. Okay, so I'm going to run this and that'll be the last.
Hi, my name is Jeff Edmonds, and I'm going to give you a basic demonstration of gate level design using Vivado with simulation. So this is, the video was recorded on my Linux machine, which does not have a microphone right now. So I'm doing a voiceover right now. That's not live. Okay, so we just opened up Vivado and we're going to open up the project. This demonstration uses a basic SR latch. So we're going to open up our source file, and you can see that there's a module that's created for the SR latch with an input S for set, input R for reset, and output Q for the output, which is placed into a register. And then we have some assignments. So if we receive an input on S, then Q is equal to 1. And then else, if we receive input on R, Q is equal to 0. So we'll go ahead and take a look at the simulation Verilog file. So for the inputs, we place the set and reset into registers, so we can assign input values, and then we assign Q to a wire for the output. That line just basically assigns the simulation to the other Verilog file. And then we start the simulation where we set set equal to 0 and reset equals to 1. And then the #1 means that we'll wait for 1 nanosecond, and then we'll set reset equal to 0, then wait 5 nanoseconds, set equal to 1, wait another nanosecond, set equal to 0, then 5 nanoseconds, reset equal to 1. And then we'll go ahead and check what happens when set is equal to 1 and reset is equal to 1, which is basically an invalid input. And then we'll go ahead and do the same for both being set to 0. All right. So before we look at the simulation, we'll take a look at the schematic that Vivado creates directly from our Verilog program. So you can see the overview here with inputs R and S, and we can expand it and see the internals. That includes, 2 inputs, 3 inputs, with one of them being ground, and then the output at Q. Okay, so we can go ahead and run the simulation now. We'll expand it so we can see it better and dive into the details. So there at the beginning, we can see that reset is equal to 1, and so Q is equal to 0. Then we set set equal to 1 and get an output of 1 at Q, and then reset set to 1, so we get an output of 0 at Q. And then when we go ahead and set equal to 1 and reset equal to 1, the simulation has chosen, has determined that this should be a 1 on the output, which in reality, we really know what should be the output. And then when we set both set and reset equal to 0, we'll also get a 1, which is what we would expect, because that's what Q was previously. And then again, go back to 1 and 1 on set and reset, which puts Q at 1, which is, basically, we don't know if that's what we want or not. That's to be avoided. Okay, so that pretty much sums up the SR, and so now we'll go ahead and go on to the half adder demonstration. So we have our half adder Verilog, and then an input of A, an input of B, an output of sum, and output of C out for the carry. Then we make some assignments where sum is equal to X or B, and then C out is equal to A and B. So this is the simulation program. So we assign A and B to a register to hold those input values, and then assign sum and C out to a wire for to hold the output value. Then just this line just basically assigns this simulation program to the Verilog script that we looked at. And then to begin, we'll start with both of the inputs being equal to 0. We'll wait 5 nanoseconds and set A equal to 1. Then wait 5 nanoseconds, set A equal to 0 and B equal to 1. Wait 5 more, B equal to 0, 5 more nanoseconds, and we'll go ahead and see what happens when we get A equal to 1 and B equal to 1. So we're running the simulation. Expand, go and dive in. All right, so at the beginning here, we got zeros all the way down because we have 2 zeros on the inputs. And we'll go and see what happens when A is equal to 1. So we get an output of 1 on sum. And then we'll set B equal to 1, which also results with A equal to 0, which also results in a 1 on the output at sum. And then go back to zeros all the way down. And then lastly, we'll see what happens when A and B are equal to 1, which results in a C out that is equal to 1, which is what we would expect. So we'll go ahead and end this video, and I forgot to show the schematic, so we'll jump back into the schematic in just a second. All right, so we're gonna create the schematic based on our Verilog code. And there's our half adder that Vivato has created a schematic for. So we have the A input, the B input, our AND gate, and our XOR gate, and then our outputs C out and sum. So I hope that demonstration was helpful.
Yes, it definitely was good. So stop sharing. Okay, so I'm going to stop the video here and then talk about some other things for the class real quickly. So stop recording. And you might want to look at this video again before your final, because it's going to be pretty much what we just talked about. And it may be more than 20 points. I'll tell you next week.